Okay, hello. Today we're going to be proving the prime number theorem. So, the prime number theorem, so basically a prime number is a whole number besides for 1, where the only numbers that divide it are itself and 1, okay? So, for instance, 7 would be prime, and by divide I mean when you take it, you get a whole number. Like, 7 is not divisible by 2 because 7 divided by 2 is 3.5, which is not a whole number. So then it turns out the only numbers that divide 7 are 7 and 1, so therefore 7 is prime. While 6 is divisible by 2 because 6 divided by 2 is 3. So there's numbers besides for 6 and 1 that divide 6. So 6 is not prime. So prime numbers are pretty interesting, and they're very important. But basically, so today we're asking ourselves, how many primes about are there less than a trillion or something? And so it turns out that there's a number called E. I mean, if you don't know what E is, you probably can't watch this video because it's pretty complex. But it's basically x divided by the natural log of x, which is the number you raise a magical number e to get x. That's how many primes there are approximately. That's the number. So say I want to find how many primes there are less than a trillion. Okay. So and we write the symbol pi, and then like a trillion, right? So like I'll show you. Trillion's 10 to the power of 9, I think. So this is a trillion, and this is pi. This pi has nothing to do with 3.14. This pi means the number of primes less than or equal to this number. And so what we're going to say is, and this is the prime number theorem, is about equal to that number, a trillion, divided by the natural log of a trillion. Okay. So like, so one thing you can ask, hey, this isn't rigorous, what does this about mean? And we're going to make this rigorous in 1 second. Basically, so for instance, I'm having a trillion divided by the natural log of a trillion. This is probably about 18. So trillion divided by 18 is about equal to the number of primes less than a trillion. And so rigorously, if we have some number x, we're going to say that the ratio between these two, pi of x divided by x over natural log of x, is going to approach 1 as x approaches infinity. Okay. So the limit as x gets really big and the number of primes less than or equal to x divided by this quantity, right, is going to approach 1, which means the ratio between them, they're not, like, you can get closer. They're not going to get, like, super close, and there are better approximations, but it's a good approximation because the ratio is in between them. Alright, so first of all, we're going to prove the fundamental theorem of arithmetic. I might have done this in previous videos, but I want to try to get us, like, sort of make this a complete video. It's probably a pretty long one, too. So let's see. So the fundamental theorem of arithmetic says that every natural number it has, not including 1, or you can sort of include 1, but has a prime factorization. Exactly 1 prime factorization, okay? So, for instance, the number 14. Well, a prime factorization is representing as the product of primes. So how could we maybe represent 14 as the product of primes? Well, 14 is 2 times 7, and you can check both 2 and 7 are prime, right? So 14 equals 2 times 7. Sorry, I accidentally drew a little dot there. So 2 times 7, and it turns out that's the only way to do it, okay? And so we're claiming that for every whole number, or every natural number, there's going to be exactly 1 way to do it. It's going to be at least 1, and there's not going to be more than 1, which means there's exactly 1. And a few technicalities. First of all, 1's prime factorization is just empty, sort of an empty set. So if you don't count that as a factorization or as a product of primes because you're not really multiplying anything, technically you could say it doesn't have a prime factorization. But we sort of count a prime factorization as just a product and no primes. But that's just technicality. And also, primes don't have a prime factorization because, like, 7 is equal to 7, and that's not a product. But so its prime factorization would just be 7. So there's a few technicalities, but those don't really matter. Right. So first of all, let's prove that there's at least 1 prime factorization for every number. Okay. So say we had a number like 63. Okay. So 63, we want to find a prime factorization. So first of all, if 63 was prime, we would be done, right? Because we would have its prime factorization would just be itself. It's the product of prime numbers. And again, there's that technicality I was talking about earlier where it's not really a product, but we're going to ignore that. So if it's not prime, and in this case it's not, there must be a factor, a non-trivial factor, and that's 3. 3 times what is 63? And that's 21. 3 times 21. And now we can repeat this process again. Are both of these numbers prime? Well, if they were, we would have a prime factorization, right? And it would be represented as the product primes. But if they're not, like 21's not, we can sort of decompose it even more. And we get 3 times 3 times 7. Right? And so, yeah, so basically you see, we split apart. If another one of these wasn't prime, we would split apart repeatedly. I mean, you can only get so many numbers because every number is going to be bigger than 1, and eventually, if you had like a trillion numbers here, it would have the smallest it could be is 2 to the power of a trillion, which is way bigger. So eventually it'll have to stop, and at this point it stops for 63, and all the numbers are prime. Okay. So every number you can sort of do this factorization tree, which maybe you learned in school or something, to find at least one prime factorization. So the real fun part of the fun theorem of arithmetic is proving that there's only one. Okay. So now we're gonna assume I had some number n that had 2 prime factorizations. Okay. Which meant, let's say it has p1 to the a1 times p2 to the a2 times p3 to the a3. I don't know. Let's say p5. This is only like one example, but say like I only included 3 terms, but say we just had some number n. Actually, I'm not going to do it with variables. I'm just going to go through an example, and the example applies to every possible case. So if I had a number like 3 squared plus 5 times 7, if that was prime factorization, so if there's a number n that has 2 prime factorizations, then one of the prime factorizations could be, let's say, 3 squared times 5 times 7, and the other could be 3 times 11 times 13. And if you actually check these numbers, you'll see, oh wait, that's not true. But basically, this is just an example that we're using with real numbers to see how for all cases we would get it. Alright, so basically, if these two things were equal, if you ever had 2 prime factorizations that were equal to each other, and this is just an example with real numbers, because none exists, I can't show you a real example of this happening. So just pretend these are equal. Then what that means is we check, is there a number that appears in one of these that does not appear in the other? And in this case, yeah, there is. 5 appears here and does not appear here. But if there wasn't one, like let's say, like they must differ in at least one place for them to be different prime factorizations. So say one, so maybe I should cut that part out. I don't know. So say I had 2 different prime factorizations of the number n. Okay, so they're equal and they're different. Now, for them to be different, which we just said, they must differ in at least one place in the prime factorization, which means at least one prime number must appear a different number of times. Let's say it appears 4 times in the first prime factorization and 5 times in the second. Okay. Now we divide both prime factorizations by that prime to the 4th power. Okay. Now, because we're dividing both, it's still equal. So now I have a prime factorization with 0 and a prime factorization with 1, right? And you see now this one has no prime, none of that missing prime in it, right? And this one has exactly 1, right? So we see in this way, no matter if I have 2 different prime factorizations for a number, we see that we can sort of get to a point where the prime is in one prime factorization and it's not in the other. Okay, so for instance, 5 could be in the first prime factorization and 5 is not in the second one. Now, because 5 is in a prime factorization, that means 5 times a bunch of stuff is your number n, which means 5 divides n. But because the second prime factorization is also equal to n because they're equal, they're both prime factorizations of n, 5 must divide the second prime factorization. So now we have some product of primes. And it doesn't have to be 5, but I'm just going to use the number 5. But, so, and we know that 5 divides this, where none of these guys are equal to 5. And again, how we did that is, if I have some number n, which has 2 prime factorizations that are different, I basically look for a place where they're different, whichever one it appears the least in, I divide by that amount, so that all of that number disappears in this one, while there's some left in here. because there's some left in here, that number must be divisible by that number, or by that prime that was different. Meaning that because these are equal, this one also has to be divisible by the prime. So now I have a prime that does not appear in here, but it divides this product. And so we're just going to assume it's 5 just for a nice number, so we don't have to like always use variables. Although it works for any prime. So fit 5 times this stuff. Okay, so now what we're going to do is we're going to make a chart, okay? Does 5 divide P1? Does 5 divide P1 times P2? And etc., okay? Alright, so here is our chart, okay? So, and we're gonna basically see eventually, so first of all, the first thing must be false, okay? And the reason for this is P1 is a prime, which means it's only divisible by itself in 1, but because none of these primes are 5, and 5 is not 1, 5 is neither that number or 1, so 5 cannot divide it. So the first one we're going to put in X, okay? It's false, it has to be. Also, if there's like only one here, that's impossible because the last one has to be 1. Anyway, so the last one we know is true because right here we wrote it. So the last one's a check mark. So then at some point here, it has to switch from being an X to a check mark. So let's say that, and that switch can occur anywhere in between here. Let's say it switches from here to here. There must be some point where it was an X and then it was a check mark. So let's say this is, it doesn't have to be exactly this one, but there's something like this. It goes from X to check mark right here, okay? So 5 divided this, sorry, 5 did not divide P1 times P2, but 5 did divide P1 times P2 times P3. Also, this is a technicality, but if there's only one number in this list, it's impossible because the last one has to be a check mark and the first one has to be an X, so we can't be both. But that doesn't really matter. So now I have, so 5 does not divide this number. I'm multiplying it by P3, and 5 now divides the product. But P3 is a prime, so it's only divisible by 1 in itself. 5 is not 1, and 5 is not P3 because remember, none of these primes are 5. Okay? So, let's see. So 5 did not divide this thing. Let's call this thing A. 5 did not divide this thing, P3. Well, now we're going to call it B. But 5 did divide their product. Okay? So 5 did not divide A. 5 did not divide B. But 5 did divide AB. Right now. So let's see. Right here. Okay? And remember, 5 can just be any prime. It doesn't matter. Okay? So now what we're going to do is we are going to... Okay, so first of all, we're going to look at the multiples of B and see which of them 5 divides. So 5 divides 0 times B, right? Obviously, because 5 divides 0, right? And 0 times B is obviously 0. So, and then we're going to, maybe 5 divides B, maybe it doesn't. Well, actually, we'll come back to that. 5 maybe divides 2B, maybe it doesn't. I'm just going to put question marks. Okay, here's what it says. So, we know it divides this. It maybe divides this. It maybe divides this. Well, can we think of two numbers that must divide? Now, 5 obviously divides 5b, so I'm going to put that down, right? At some point, 5b is going to appear here, right? So 5 divides 5b, we know that. Also, 5 divides ab, okay? 5 divides ab because guess what we just wrote back up here? 5 divides ab. What? So, let's say we go through the multiples of 5, and let kb be the first non-zero multiple of b that 5 divides, okay? So, now, what we have is k... So let k be the smallest number, and obviously k must exist, because if all else fails, maybe like pb, or sorry, 5b could be the first multiple, if there is nothing smaller, right? So there must be at least... k must exist. Because you can always take the minimum of like a finite set that has non-zero element, or not zero elements in it. Oh, okay, so now, say we have, say we want to look at all the other numbers. So say kb is the first non-zero multiple of b that 5 divides, okay? Now, let's see, so this 5 must obviously divide 2kb, right? And 3kb, etc., right? And remember, 5, at the end of this argument, you should be able to replace every time I said 5 with just the letter P for any prime. and the argument still holds. I'm not doing anything special with the number 5. It's just any prime word. Alright. 5 divides all these things. So the question is, say there was some number L, okay, which was not a multiple of KB, okay? So let's say, so it must have a non-zero remainder. Let's say A is equal to KB plus R, and that's the remainder when you divide by K. Okay, we're saying there's some number L that is not divisible by K, so it must be, or sorry, wait, I should not use that number B, sorry. Let's say L is equal to KX plus R, okay? So R is the remainder when you divide by K, okay? So what we see here is, and we want to check is, so L is any number that's not a multiple of K, because we're saying R must be non-zero then. So we want to check is LB divisible by 5. Alright, well let's look at that. Okay? LB, we're multiplying both sides by B, is equal to KBX plus RB. Well, let's see a few things. So first of all, this is obviously divisible by 5, right? So right, because it's a multiple of KB, and KB is divisible by 5. RB is not divisible by 5, and here's the really cool part of the argument. Because RB is smaller than KB and R is non-zero, if RB was divisible by 5, R would be the smallest, or a non-zero multiple of B that 5 divided that was smaller than K, which is impossible, because K was the smallest. Therefore, this cannot be divisible by 5, okay? So if this was divisible, then you would have a divisible thing, something divisible by 5 is equal to another thing divisible by 5 plus something that's not, which would mean this is a multiple of 5, or sorry, so then you can subtract this from both sides. You have a multiple of 5 minus a multiple of 5 is not a multiple of 5, which is impossible, because like 5a minus 5b is going to be 5a minus b, which is still a multiple. So therefore, we arrive at a contradiction. So therefore, LB cannot be a multiple of 5. Okay, so therefore, we know if L is any number that is not divisible by K, it cannot be a multiple of 5, okay? Now, here's the really cool part, right? So 5b is divisible by 5, right? So in that case, L would be 5. So because we just said if L was not divisible, no, sorry, if 5 was not divisible by K, then that means that 5 would have to, right, then 5b could not be divisible by 5, because we just said if a number is not divisible by K, then that number times b is not divisible by 5. So therefore 5 must be divisible by K. Okay, so we can put K divides 5, and also same thing for AB. If A was not a multiple of K, then AB cannot be divisible by 5, but we know it is. So, K divides A, okay? So, now, what are the divisors of 5, okay? So the divisors of 5 are 5 and 1, right? Or let's say 1 and 5, it doesn't really matter the order. So since K divides 5, K is either 1 or 5. If K is 1, remember, K is the first non-zero multiple of B that is divisible by 5, therefore 1 times B would be a non-zero multiple, or 1 times B would be divisible by 5, which means 5 divides B, which is impossible because of right here, right? If the other possibilities, K is equal to A, right? Yeah. No, sorry, K is equal to 5, right? That's the only other number that divide 5. But then we have K divides A, and if K is equal to 5, that means 5 divides A, but right here we have 5 does not divide A. So we have reached contradiction. And we got to this contradiction assuming that there were 2 different prime factorizations, and so therefore there cannot be 2 different prime factorizations, QED. Okay, so now we're going to use this, so now we're going to use this fact that there's exactly 1 prime factorization. We're going to talk about a new function, the Riemann-Zeta function. So basically, if I have some number, so here's an interesting thing I'm not really gonna prove, but basically, if I have the sum from n equals 1 to infinity of 1 divided by n squared, and I sort of sum this, or I just sum 1 over n squared from all integer values of n from 1 to infinity, then what do you think it's equal to? It's actually equal to pi squared divided by 6. Which seems really just out of nowhere. I'm not going to prove that in this video, it's just an interesting result, okay? So what if we replace a number squared with s? Say now we're talking about the function n equals 1 to infinity of 1 over into the s, okay? And we're going to give this function a special name. So we plug in an s, and our output is the summation from n equals 1 to infinity of 1 divided by into the s, okay? And we're going to give that function a special name, the Riemann-Zeta function, okay? And that's going to be very important to our proof of prime number theorem. So right here, we have the Riemann-Zeta function. This isn't the actual symbol for it, but I can't draw the real symbol, so we're just going to go with this weird E thing. The Riemann-Zeta function of s is equal to summation from n equals 1 to infinity of 1 divided by into s. So one thing we can ask is, where does this thing converge, okay? Now, the thing is, we can see first where we know it. Well, I guess I didn't prove it. I just told you that it converges to n equals 2 and it's equal to pi squared divided by 6. But first, let's just say, how should I do this? Alright, first let's say prove it does not have a value at 1, okay? If I plug in 1 to this, it does not work. Alright, so what would z of 1 be, okay? Well, that would be summation from n equals 1 to infinity of 1 over into the, well, if s is 1 over into the 1, or just 1 to over n. So now, there are many proofs that this diverges, goes to infinity, which means if I plug in 1 to the Riemann-Zeta function, it won't work, it'll just go to infinity. I'm going to go for a more complex proof than the simplest one, because we're going to use something similar later to prove that other values do not diverge. Okay, so we have a function called, alright, so say there's something called an integral, which is basically if I graph something, the integral of that between the values of a and b. Also, earlier I used a and b for like p divides ab or something. We're not doing that now. That's completely different representation of those letters. So if I have numbers a and b, the integral of a curve between a and b is basically the area under the curve. All right, and this is calculus. And if you don't know this, you might not be able to watch this video, but maybe you can. So let's see. So we have the integral. So first we're just going to look at the integral from 1 to infinity of 1 divided by x dx. Which means if I graph the function y equals 1 divided by x, and I put a little marker at x equals 1, and I can't really put a marker at x equals infinity, but I put one way over here at x equals infinity, and then I add up all the area under that curve, between that and the x-axis. That is what this integral is going to be equal to, okay? So, by the, I think, fundamental theorem of calculus, right? I guess I should prove that. I'm not going to be like, I'm not going to prove that because it's sort of, I don't want this video to be like too long or something. I don't know, but anyway, it turns out that you can prove there's a function called the natural log of x, and the derivative or instantaneous rate of change of the natural log of x is 1 over x. So according to some theorem called the fundamental theorem of calculus, I think, the integral of the derivative of function from a to b is that function at b minus the function at a. So we're taking the natural log of infinity minus the natural log of a, or natural log of 1. Now natural log of 1 is 0, natural log of infinity, you remember a long time ago I said that natural log is the number you raise e to get infinity. You have to raise e to power infinity to get infinity, so so therefore the natural log of infinity is infinity, so we have infinity minus 0 is infinity. So let's just, right. So therefore this thing is infinite, okay? So there's another thing where basically, so this is quite similar to our sum here, right? It's not exactly the same, because in the other one you can imagine I was summing like discrete things. Here I'm sort of smoothly like taking the area, but I can sort of connect them. So for instance, if I graphed the function 1 over x, and let's see, what? Yeah, so should I do it like that? Yeah, okay, so I guess I drew this poorly, sorry. So I'll start here, I see. So I'll do it like this, I think. Right, so this would be sort of, each of these has sort of length 1, although I accidentally drew this one smaller. So basically, It has a length 1 and a height of like 1 over x. So if I sum up all these little rectangles, I'll get this. But you can see it's bigger than this integral. It's bigger than the area under the curve from here to infinity. Therefore, it's bigger than infinity, so it's infinity. Therefore, this thing does not diverge. But I can do something similar for other values. Say I had like 1 over x to the let's see. Yeah, so say I had like like zeta of some number a that was larger than 1. Okay. So then what I can think about is comparing it to the summation, or sorry, the integral from, wait, I'm not sure. Yeah, I do need to do this. Okay. So say I took the z of a, I would have the integral, or that would be the summation from n equals 1 to infinity of 1 over into the a. Okay. Right. So then I can compare it to the integral from 1 over infinity, which is similar but not exactly the same, of 1 over x to the a dx. And then it turns out if a is bigger, if a is bigger than 1, I think, well, basically 1 over x to the a is x to the negative a, and if a is bigger than 1, right? Yeah. Then the antiderivative of that, the thing that would evaluate infinity in 1 would be, I think it's x to the negative a plus 1 divided by negative a. And you can see if I take this derivative of this, if you know, like a power rule or something, unless I mess this up. Oh wait, no, I do it. Alright, so here, if I took the derivative of this, it would end up being x to the negative a. So if I evaluate this thing at infinity at 1, I get this. Now at 1 it's just inside the value. I don't care. At infinity, because x goes to infinity and a is bigger than 1, it's big numbers to the power of negative, which goes to 0. So this thing goes to 0, so it's 0 minus infinite. So this thing is finite. Okay, for a larger than 1. And again, I can sort of compare it. If I do it this time, remember back here when I was comparing it to the first one, like here, I basically, it was all bigger. So if I did the exact same thing, that would be dumb, because it would prove that it's bigger than a finite thing, which says nothing about whether or not it's infinite. But what I can do, I can shift what term it's related to. So like, if I pulled this, if I sort of shifted everything, then this would match to here. This one would match to here, and etc. And I would actually be able to contain the entire thing small within that area, not including the first box. Okay, so I'm not a good enough drawer to like draw this, but basically, if you imagine I have my curve, right, and then I have like my boxes, yeah, right, and then I sort of shift them over so that each box is sort of in point is where it touches the curve. If you draw this out and you like understand like what I'm saying, then like it'll all fit under the curve. Therefore, this infinite sum is smaller or equal to the integral under the curve, except for the first box, which is sort of pushed out of the integral. And if the integral is finite, it has to be finite. Yeah. Okay, so therefore, for a greater than 1, it will be finite, a finite number. And for a equal to 1, it will explode to infinity. What? Now, I'm not going to go into exactly like how you introduce raising numbers to complex powers, but it turns out there's a cool way to do that. But basically, if I raise a number, it comes from that number e again. Basically, if I have e to the I theta, it's cosine theta plus I sine theta, which basically, if you imagine, if you know the complex plane, and I go sort of mirrored on my computer. So, if I walk around the unit circle some amount on the complex plane, however much I say I walked like 1 unit around it, like to here, or around like here, I can draw this. If this is complex plane, and this is a unit circle, and I walk like 1 unit around here, then that's going to be equal to, that point right there is e to the I. If I walk 2 units, this point right here is e to the 2i. And then using natural log and stuff, you can actually define this for every number. Okay, so you can raise numbers to complex powers. Okay, so let's see. Well, so basically, since we can do that, and this is just a sum of that, we can basically write this function for values, for complex values. So we can put in 1 plus I, and we can get 1 over 1 to the 1 plus I, plus 1 over 2 to the 1 plus I, right, etc. So now the important thing here is that if I have some number and I raise it to some power, the real part of that would determine the sort of the absolute value. So like 2 to the 5 plus I has the same absolute value as 2 to the 5 plus 2I, okay? So therefore, this function, if I, for instance, plugged in a complex number, like, let's say, 1/2 plus I into this function, oh, sorry, not 1/2, 1.5 plus I, z of 1.5 plus I would be 1 over 1 to the 1.5 plus I plus 1 over 2 to the 1.5 plus I, right? Yeah. Okay, so, and the absolute value of each of those terms would be the same as the original, but because the original converged, and because in the original it was sort of the maximum possible value you could ever reach where they're all pulling in the same direction, now they're even just fighting each other because they're all pulling in random directions on what the sum is going to be equal to, so it also has to converge. And this, so therefore we know if I have a complex number with a real part bigger than 1, real part bigger than 1 must converge. But this doesn't quite work for the reverse argument. Doesn't work for the value of 1. Like 1 plus you can't really prove that this thing will go to infinity, right? Because true, they'll have the same absolute value in each place, but because the 1, because it went to infinity when 1 plus 1/2 plus 1/3 plus 1/4, which is the Ramsey function 1, they're all pulling in the same direction, right? Or towards like infinity, right? But now they're going to be fighting each other and canceling each other out, and it turns out, so we don't know, maybe it goes to infinity, maybe they still are strong enough to pull to infinity, but maybe they're not, maybe it actually converges. I think it does end up converging, but yeah. Right. So for now, we're just gonna know it definitely doesn't converge at 1, and it converges at any complex number with real part greater than 1. So if we drew the complex plane, this is my complex plane, and I should put a little dot. And this is 1. It does not converge here, but everywhere around here it does. Okay. So let's see what else. Oh yeah. Now the entire part. Remember, like a few minutes ago, when I showed you the fundamental theorem of arithmetic, that everything has unique prime factorization. Well, there's a reason I showed that to you, and it's because, well, you're about to see. Okay. I only got 2 pieces of paper, so I'm going to keep on drawing this one for a little while. Let's see. So let's assume A is a complex number with real part greater than 1, so we know it converges, and moreover is absolutely convergent. And if you don't know what it means just means the sum of the absolute values of those terms is finite, which we know because that's just its value when it's a real number, right? So like, for instance, z of 2 plus I is absolutely convergent because the sum of the absolute value of those terms just is z of 2, which is plus square root of 6. But so let's see. So if I have the summation from n equals 1, and remember this is z of a, where a is a complex number with real part greater than 1, to infinity of 1 over, let's see, into the a. I think it's more traditional to use the letter s, but it doesn't really matter. Let's see. So we're gonna write this out. So first, we have this, and we're just gonna expand it. So at the bottom of my page, I'm gonna write. So this is obviously equal to 1 to the a plus 1/2 to the a plus 1/3 to the a plus 1/4 to the a, etc. forever. Okay. So then what we have is, so let me think. And obviously 1/4 to the a is just 4 to the negative a, the basic properties of exponents. So I'm just going to rewrite this again with 1 over 1 is still 1. So 1 to, yes, so it's still 1 to the negative a. The first term, the 1 to the power of anything is just 1, it doesn't really matter. So that term, it doesn't really matter how I write it. Plus 2 to the negative a, plus 3 to the negative a, plus 4 to the negative a, etc. So this is equivalent. So right here, now what I can do is I can take each term, and because it has unique prime factorization, if I could somehow, if I could, for each prime number that existed, choose sort of a number of times it would appear, like I could say, okay, I want 6 of 6 2s in my prime factorization, no 3s, 1 5, no 7s, something like that, and then that number appeared in here exactly. So once, well, I'll show you where this is going. Okay, so say I took, yeah, this is the way to do it. Say I took all the powers of 3 to the negative a. Okay, so I had 1 to the negative a, plus 3 to the negative a, plus 9 to the negative a, plus 27 to the negative a, etc. Okay. Alright, so let's see. And I multiplied this by all the powers of, and I just randomly skipped over 2, I just chose some other numbers. All the powers of 5 to the negative a, right? So 1 to the power of 5, 5, 25, 125, etc. Now, what would I get if I multiplied this? Well, by basically the definition, or maybe not the definition, but basically how you expand if you multiply products of sums, it's basically the sum of all possible combinations, right? So I would get this term times this term would appear once, right? Also, this term times this term would appear once. And so I basically get the sum of all possible combinations, which are all powers of 3 to the negative a times all powers of 5 to the negative a. So I basically get, I basically get the sum of all possible powers of 3 to the negative a times all possible powers of 5 to the negative a. Okay? That's what this would be. So now I'm going to do it over all primes. Okay? And I think this is yet another representation of pi, not pi the number, not pi the number of primes less than or equal to x. This pi right here is the product symbol. It means, and I put a little p under it, this means I'm multiplying whatever I'm going to put here for all primes. So if I put 1 to the negative a plus p to the negative a plus p squared to the negative a plus p cubed to the negative a, etc. So what would this be equal to? So I have this value, right? Here I was multiplying this thing for the primes 3 and 5, but now I'm multiplying for all primes. So I'm basically it's going to be the sum of all possible numbers that are, it's going to be every combination I could have. So every possible value I could have chose for 2. So every possible power of 2 to the negative a times every possible power of 3 to the negative a times every possible power of 5 to the negative a times every possible power of 7 to the negative a, etc. Right? So this might be confusing, but like, don't worry, it's just sort of complex, but eventually I'll get it. So let's see. So basically, this is the sum of, let me think. And also, the name of this thing that I'm showing you is like Euler's product formula. Euler invented it, I think. Maybe sometimes stuff isn't named after people who invented it, but so basically this would be 2. Right, so what would appear here? Okay, I got that. So basically, I had all possible powers of all the primes to the negative a, so they're all possible combinations. So I have 2 to the m1 times 3 to m2 times 5 to the m3 for all possible values. This represents all combinations I could ever get in the sum, and every one of them, the sort of negative a's combine, and I just get to the negative a. Yeah. Okay. So, but here's the thing: there's a one-to-one correlation between combinations of primes and the natural numbers, because every product of primes is a natural number in exactly one way, and every natural number is a product of primes, which is what we proved earlier, in exactly one way, right? Alright, so every natural number is going to appear in this sum exactly once, which means what I'm really doing is I'm summing all natural numbers to the power of negative a. So 1 to the negative a will appear once, 2 to the negative a will appear once, 3 to the negative a will appear once, etc. So that's the beauty of this thing. And that, if you remember, is z of a. So therefore, this thing right here, we're not even done simplifying this. This thing right here is equal to the Raymond zeta function of a. Okay. So now we're going to use a property. Well, let's say just easy exponent property. A number to the power of 7 to the power of 30 is the same as that number to the power of 30 to the power of 7. Right here. So, for instance, here p to the power of 3 to the power of negative a is p to the power of negative a to the power of 3. And we're just going to rewrite this thing as p 1 to the... Also, the 1 to the negative a term, that's 1 to anything is just 1. So I'm just going to write that as 1, okay. Well, so this is equivalent because we just switched it around and then we replace this with this because it's equal. Now, if you know, it's sort of bright. I don't know if you can see the page. Okay. So basically, let's see if I'll adjust. Oh, there we go. Alright, so we're taking this sum, and if you know the infinite geometric series, you know, because this thing is like, right, it converges if the ratio it has an absolute value smaller than 1, and obviously the ratio here is 1 over p, because p, like, we're basically doing p to the negative 1, p to the negative 2, or p to the negative 3, p to 0. Forever, which is just 1 over p to all the numbers. So it's an infinite geometric series with 1 over p. So it's 1 over p plus 1 over p to the a. Sorry, I got it backwards. So it's 1 plus 1 over p to the a plus 1 over p to the a squared plus 1 over p to the a cubed. You can see, like, for instance, this term p to the negative a is 1 over p to the a, so that cubed. So therefore, I have the infinite geometric series with 1 over p to the a. Now, the infinite geometric series is equal to 1 divided by, or the first term times 1 divided by 1 minus the ratio. First term is 1. That 1 divided by 1 minus the common ratio is 1 over p to the a. So we have, this infinite sum is equal to 1 divided by 1 minus 1 over p to the a. Okay. Yeah. So 1. Okay. And now this is Euler's product formula. It's much better looking than like this theory form. Okay. The light is so bright. I don't know if you can see it. And so this is why this function is important to us, because it relates normal numbers to like the primes. Okay. So now we have a function that deals with the primes and the natural numbers. We had the natural numbers in the beginning, we're summing over all natural numbers, and now we have a product formula that deals with the primes, and that's why this function is so important. Okay, let me think. Okay, so I'm doing that. Well, let's bring up the proof. So the proof I'm using, that's just like trivial stuff about the Raymond zeta function, or maybe not completely trivial, but I don't know. So basically, the proof I'm using, I'll read out the HTML thingy. I'll probably include in the description too. It's people.mpim slash, or not slash dash bonn.mpg.d Zagier files DOI, and then like a bunch of I'll just put it in the description. And it's called Newman's short proof of the prime number theorem by D. Zagier, dedicated to the prime number theorem on the occasion of his 100th birthday. So this is a very short and nice proof of it. It's still really complex. They just compressed the density of the complexness, so it's really short and really complex. Let me go back here. Okay. So the next step here is, so remember how I said that the Raymond zeta function is not defined for, like, right, so say, yeah, so say I plugged in a is equal to 0.5. Now obviously 1 over the square root of 1 plus 1 over the square root of 2 is 1 over the square root of 3, etc. diverges, because this is zeta value that's even smaller than 1, so it's even bigger than infinity. So, but we're wondering if there would be a way to redefine the zeta function so it's exactly the same everywhere we've already defined it, but it's also defined at a point like 0.5, okay? So how you do this is with analytic continuation, yeah, okay. let's see if we go here. So what we're gonna do is we're gonna now look at the new function, the Raymond's, and I'm gonna stop using the variable a and I'm gonna use s because like s is more normal. So we have z of s minus 1 over s minus 1. Let's see. So we have this new very similar function where we're basically taking the Zanda function and then subtracting this. And what we're going to do with this is we're going to use properties of sum and integral and sort of combine terms and redefine it, okay? In a better way where we redefine it and sort of cheat our way into finding cool new values that allow us to do cool stuff. Alright, so let's see. So first of all, the zeta function, as we already discussed, right now we're not going to use the product formula, that's important later, is a summation from n equals 1 to infinity of 1 over into the s. Right here. That's the first part. Now, if you know calculus, you'll know, well, 1 over s minus 1 is, let me see what they did. I don't actually remember what that is. So it's an integral from, yeah, that makes sense. 1 to infinity of 1 minus x to the s dx. Okay. And you can check this. The antiderivative of this would be, let me think, x to the negative, x to the negative. Would it be s minus 1 or s plus 1? That's weird. Oh wait, I see. Yeah, I get it. Okay, so for instance, the antiderivative of 1 over x to the s would be, I think it's x to the negative s minus 1 divided by negative s minus 1. Right. Hope so. Yeah. No, it's I see. It's x. The antiderivative of 1 over x to the s is x to the negative s plus 1 divided by negative s plus 1. Alright, so this is the antiderivative, so we evaluate this as 1 infinity and infinity. Right now, right now we're at the beginning. We're only talking about values with real part greater than 1. So this thing, so this is a number that, right? So then if s has a real part, right, yeah, if s, so we only care about values of s with real part greater than 1. So therefore, negative s has a real part less than negative 1. So negative s plus 1 has a real part smaller than 0. So you're raising very big numbers to negative powers. Sorry. It means that dividing by some constant thingy means that this thing is going to go to 0 at infinity. So at infinity, this thing's 0. So now we just need to subtract this value at 1. At 1, we have 1 to the power of something. It's 1. 1 divided by negative s plus 1. So we're subtracting 0 minus 1 divided by negative s plus 1. This is what our integral is going to be equal to now. Obviously, so obviously, because the negative it cancels out. So now we multiply negative on this. This way, basic algebra stuff. We get 1 over 1 minus. Did I miss this out? No, that's good. So, and then that's 1 over s minus 1. Alright, so this thing, we just evaluate this integral and saw it's equal to this. And right now we're only dealing with values of a, or sorry, no, we're using the variable s, with values of s with real part greater than 1, okay? So we know that this thing is this thing, alright? And now we're going to combine the sum and the integral, okay? So let me think. Well, let's see how you did it. He's good. So basically, we're going to sort of take it in chunks. So if you imagine, one of the terms we have is basically summing 1 over into the s, and the other one we have is taking the integral of 1 over x to the s, and the variable doesn't matter. In an x, it doesn't really matter. So basically, we're going to do this sort of piecewise, not like. So we're basically taking from 1 over into infinity of 1 over into the s, which is our first part. But then within this, we're sort of dividing up the integral into chunks and pairing it with our zeta function. Okay. Let's see. Let's see if I can get it. Yeah. Right. So, let me just go back to, give me 1 second. Where is it? Right here. So you can see this thing is equal. The first thingy is equal The second thing, we just divided it up, and we're still getting every part. Okay, so this thing's equal to that. Now, I think he brings that inside, isn't he? Yeah, he is going to do that. So now what he's going to do... I wonder if there's a way to... is he's going to bring this 1 over into the s within the integral, which is okay, because if I put 1 over into the s as a constant, and the size of this integral is 1, so it would just be its constant value times 1, which is the same. So this is equal to the summation from n equals 1 to infinity of integral from n to n plus 1 of 1 over n to the s minus 1 over x to the s dx. Let's see, I think it's here. So now we have, I don't know if you can see this. Yeah, now we have this. Right, I think it's right here. Alright, okay, so let's see. So now what we're gonna do is we want to prove that. So now we sort of found this way to describe the zeta function or the zeta of s minus 1 divided by s minus 1 as this new thing, but it turns out this new thing actually converges. So we know that if I have a value of s with real part greater than 1, we've already proved that these two things are equal. But now what we're going to say is this new thing, it turns out we're going to prove it actually converges for real part greater than 0, and we're going to define a new version. Okay. So now we found this equality is true, where zeta of s minus 1 over s minus 1 is equal to that thing we just did. But now we're going to redefine zeta of s so that we're going to find zeta of s so the equation stays true, even with s real part greater than 0. So we're analytically continuing it. So let's see, how do we do this? So first we got to prove that even for things with a real part of 0, or anything with real part greater than 0, this thing is going to converge. Let's see how he does this. Oh, I see. Oh, so he's going to add a second integral. Let's see if I can find it correct. Alright, so right here we have this thing. So what we know so far, and I'm just going to rewrite this on the back, is that I'm going to put for the real part of s being greater than 1, we have that the zeta function of s minus 1 divided by s minus 1 is going to be equal to this thing. So we know this is true. So now, does this thing still exist if I have a value, let's say if s was 0.3, for instance. It's smaller than 1 but still bigger than 0. And it turns out yes, and that's what we're about to prove. So let's see. So first of all, we're using the fundamental theorem of arithmetic. Basically, we have some function evaluated in and evaluated x, so we can represent it as an integral. So for instance, 1 over into the s minus 1 over x to s is going to be equal to, right? And we can represent this as an integral. The integral from x to n of 1 over, well, let's see how he does it. Just double check. Yeah. S times so so right here, if you evaluate this integral, its antiderivative is like negative. Let's see. So it'll be yeah. So the antiderivative of this thing is u to the negative s divided by negative s. So if I divide that in, I get I get into the negative s over negative s. But wait, no. So the integral. Wait, I think I might have drawn it backwards. Let's see. They changed the sign. Oh, he did change the sign. That makes sense. Okay. Okay, so I miscopied what he was saying, so it turned out it wasn't true. Okay, so the antiderivative of this thing is u to the negative s over negative s. So that if we evaluate these 2 points and subtract, it's s to the negative s over negative s minus n to the negative s over negative s. Let's write it down. This thing is s to the negative s over negative s minus n to the negative s over negative s, which is, well, this is the one that's actually negative because the negatives over here and these two cancel out. This is really just n to the negative s over s minus x to the negative s over s, and that's the integral. And because we're multiplying by s, we get the s's disappear, and we get n to the negative s, which is 1 over n to the s, minus x to the negative s, which is 1 over x to the s. So therefore, these two things are equal. Let's see. I think this video's been going for about an hour, so I think I'm gonna take a break. I'm gonna upload this and I'll continue it later. Yeah, thanks for watching. Bye.